Now, we know when we say potential difference, it is V final minus V initial, the potential at the final location minus the potential at the initial location. Now, something interesting happens. Since the potential difference is independent of the path, because of that reason, if I choose the final and the initial point to be the same one, then I get, let's say if A is both the final and the initial, then what I get is 0. So to give you an example, if this is point A and you tell me I'm gonna go on a trip and I'm gonna follow this path and I'm gonna do some weird things over here, and then I'm coming back and I finish this trip back at the same point. So even though you did all of this, you took all of this path, since we do arrive at the same point, the potential difference, your final potential minus the initial potential, will be 0. Now, why is this useful? Okay, how can you use it? Here is one way that you can use it. If you know, let's say this is point B. So somebody tells you, you know what, VB, say VB minus VA is 3 volts. And to do this, I went from A to B. I took this path. Now, if I also tell you that, say this is C, VC minus VB is equal to 1 volt. Now, if somebody wants to know what is VA minus VC, then I can do the following. VA minus VC means that A is your final and C is your initial. So, from A to B, I increase my potential by 3 volts. From B to C, I'm increasing the potential by 1 volt. Okay, so far I have increased the potential by 4 volts. And if C is the initial and A is the final, and I want to know what is VA minus VC, well, I know I am doing a closed loop here. I'm arriving back at the same point. Plus 3 plus 1 equals 4. So far I have plus 4. I know when I get back to A, I need to be back at 0, back at the same potential. So if I increased my potential by 4 volts to make it to C, I need to decrease my potential by 4 volts to go to A. So VA minus VC, I know that it's gonna be minus 4 volts. Minus 4 volts. Okay, and that's because delta V on a closed loop is equal to 0.